Okay, let's talk throttle devices as well as mixers. So I have steam going through a throttle and then entering a mixer. And I have liquid water going through a throttle and entering a mixer. And both of these will mix and come out as saturated vapor at x is equal to 1, meaning all of it will be gas. And also, I know the pressure here is 20. It will throttle both initial streams to 20 psia. And I know the initial pressures. I have 30 bars and 25 bars. I know the initial temperatures, 280 and 180. And I know the flow rate of the steam. And I'm being asked for the other two flow rates. Okay. I know that my mixer is well insulated, so no heat comes in and out. I also know that nothing is moving up or down. So it's going to be negligible change in kinetic and potential energies. Okay, so let's see what we could use. So this is an open system because I have things flowing in and out. And I know from open systems, I should probably start with continuity. Okay. And I know usually I tell you to define the states. And in this case, you could, but you'll see the only thing you really need to define is H. So that's why I'm doing this first. Okay, so from the continuity equation, and this is not just one stream in and out, I have to account for all streams. I know that all my entering streams, my initial streams, will have to equal all my exiting streams. Oops, ME. So my flow rates coming in have to be my flow rates coming out. So that means that M1 plus M2 have to equal M3. Pretty trivial. That's what the thing tells us. Makes sense. But you'll see we will actually need it. So in this equation, we can solve this equation. We want both M2 and M3, and we only have M1. One equation, two unknowns. That's not good. So we will use this equation in a minute, or a few minutes. The other equation to use is first law, open systems. And again, under steady state. So when I have mixers and things like that, you can assume steady state. And since we don't have any kinetic energy or any potential energy, there's no heat loss, there's no work being done. What I'm really left with, and I could show you. We have Q minus W usually, and that's usually equal to the change. So I have all my entering streams. I will say M I of 8 with HI. Oh, I guess no. I'm sorry. It's exiting stream. Exiting stream minus the change in exiting stream in initial stream of MIHI. This is an I. And then plus the change in kinetic energy that way, change in MI, I guess I'll keep doing that, MEKE exiting minus the change in MIKEI plus all the potential energy exiting minus the potential energy leaving. Coming in, I'm sorry, keep doing that. Okay, so basically it's the change in kinetic energy, potential energy. Since we know that these go away, we don't need this. Since we know there's no heat and work, we don't need this. So what we're left with from the first law is that 0 is equal to all the exiting streams, M dot E, H E, minus all the entering streams. Yes, all the entering streams, M I dot H I, for all entering streams, for all exiting streams. That's what that's telling us. And so our exiting streams is only one, it's M3, and our entering streams are M1 and M2. So let's apply that. So from the first law, we get that 0 is equal to M3 dot H3 minus the sum of what's coming in, M1 dot H1 plus M2 dot H2. Okay, that's really it. And if you rearrange that, you get M1 H1, M2 H2 is M3 H3. And the other equation we have is just M1 plus M2 is equal to M3. So I'll write that right on top. Okay. So those are the two equations. One we get from the continuity, and one we get from the first law. So one from the conservation of mass, one from the conservation of energy. Okay, so I'm going to point out what we have. We have M1, and seems to be that's it. Okay, so we do know that right here we have some steam. So we could go to the steam table and try to find H1. So you go to H1, you try the superheated steam table, and you go under pressure of 30 and temperature of 280, and you find that your H1, if you look at it here, is 2941.3 times 10 to the third joules per kilogram. Okay, so we have H1. We also know that this thing is saturated vapor. And with saturated vapor, with X is equal to 1, you can go to the saturated table and look at Hg. Whatever Hg is, that's the H, because there's no liquid at all. So HF is not coming in to bother us here. So we know that H3 here is 2799.5 times 10 to the third joules per kilogram. Okay. We also know here that this is a compressed liquid scenario. So we can go to the compressed water table and find its enthalpy. And when you do that, you find that it's 763.97 times 10 to the third joules per kilogram. Okay. So now we have the H's. We have this H here, which is good. And we have H here, H here. Now, are these H1 and H2? That's the question. I'll call it H1 prime and H2 prime. Because I'm going through a throttle. And so I'm changing the pressure from 30 to 20 and here as well. So the question is, and this is totally a reasonable question, if I'm supplied into, whatever I'm making here, I'm mixing two liquids here, two fluids here. When I'm mixing two fluids, I can sometimes get them at different pressures than I need, and I have to change the pressure or the temperature or whatever. So when I do that, and the temperature will invariably change here as well. So we'll probably have a different temperature and pressure here, a different pressure and temperature here. But because I'm doing it through a throttle, what I know for throttles is that delta H is equal to 0. This is isenthalpic. So that means that this H1 prime is actually H1 and H2 prime is actually H2, because they will be the same here and here. They don't change because it's a throttle. So I don't really care what it looks like here. And I could figure it out if I was asked for the temperature, and we can find the temperature here, no problem. And we could do a worked out example of the actual temperature change in this scenario and actually figure out what this temperature is. But we're not being asked for it. We're specifically asked for the mass flow rates. But just from this information alone, we can figure out the temperature of this stream using just simple heat transfer and get this temperature. But we're not asked for this. We just asked for the two flow rates. Okay, so I know now that this H1 also corresponds here and H2 also corresponds here. So if I go here, I actually know H1, I know H2, and I know H3. So the only thing I'm missing from both equations are M2 and M3. So that's good. I have two equations, two unknowns, and I can solve for it. So you can put in the actual numbers into this, and then solve one for the other, and you find that M2 dot, if you do this correctly, and it's just punching in numbers at this point, so I'm not going to show you this in great details. I trust that you can do it. You find that M2 is equal to 0.38611 kilograms per second, which is equal to 1390 kilograms per hour. Now, why did I do kilograms per hour? Because this initial one was given to me in kilograms per hour. So you probably should change that to kilograms per second before solving it, so everything kind of works out, because you want to stay even the SI, although I don't think it matters here. And then you can get M3, which is just the summation of M1 dot plus M2 dot from here. Oops. M3 is just a summation of these two. So it will be 1390 plus 20,000. It will be 21,390 kilograms per hour, since mass is conserved. So there you go. Now, like I told you, we figured this out, and at this point, we are well equipped to also find the temperature. So if I was asked for the temperature, there's another question asking me for the temperature here. Okay, then I know the H here, and I know the pressure here, 20. I would go to the table and find the appropriate table that corresponds to this pressure and this enthalpy. And I would find out the temperature here. Okay, so we'll call this T1 or something. So we'll call it T1B, I guess, because 1A will be here. And I will do the same thing here. I would find T2B. And I don't know the temperature here, but I could figure this out also from the fact that it's saturated. But if I did not have that piece of information, I could use the fact that I have two mass flow rates coming out, and I have a mass flow rate coming out this way, and use these temperatures to figure out that temperature using the correct MCP to T.